Okay, welcome back. Now we're going to introduce the next theorem because in the previous example we used a function that had a rational exponent. So now what we're going to do is expand the power rule to include rational exponents. So it says the power rule may be extended to rational exponents. That is, if n is a positive integer, then the derivative of x over 1 over n, or we could look at these as the nth root of x, right? So x to the 1 over n power is equal to 1 over n. So you take the power, drop it down, and then you reduce the power by 1. So again, we're just extending it to rational exponents. Also, we can also use this for any rational exponent. So we can say also if n is a positive integer and m is an arbitrary integer, then we can apply the same rule to this situation. The derivative of this function with respect to x the derivative of x to the m divided by n power, right? So with respect to x is equal to, again, we drop the exponent down, m over n, and then we reduce the exponent by 1. Okay, so now let's do the proof of this. Okay, and to prove this, we're going to use the inverse. So here's the proof. It says let n be a positive integer. Okay. Let's start by taking the function x to the 1 over n power. So given or let g of x equal 1 over, or no. Not that. X to the 1 over n power. Okay, so now we're going to use the inverse function. So the inverse, right? So f of x equals g inverse of x equals x to the n power, right? And so we start by taking the inverse of f of x, or not the inverse, but the derivative of f of x. So f prime of x equals, well, it's just the power rule. N times x to the n minus 1, right? And so then if we put in g of x, then what do we get? We get f prime of g of x equals n to g of x to the n minus 1 power, right? Which then equals n times x to the 1 over n raised to the n minus 1 power. Then we're going to use the power property, one of the power rules for exponents. So this is going to be n, and what do we get? We're going to multiply exponents. So we get x to the what? N minus 1 over n So now that we found the inverse, and now we've got to, excuse me, use the fact that g prime of x is equal to 1 over f prime of g of x, which is going to be 1 over n x to the n minus 1 over n. Which is equal to well, hold on a second. That's not right. This is 1. 1. I didn't multiply right. So 1 over n times n is not n, it's 1. So this is correct. Okay, so now, what do we do here? Now, all I'm going to do is I'm going to put the x into the numerator. So I'm going to write this as 1 over n x to the, now it's going to be negative 1 minus 1 over n, which then gives me the result of 1 over n x to the 1 over n minus 1, which is the result that I wanted. Okay. Now, similarly, what if we have m over n? Well, if g of x equals x to the m over n, I'm going to rewrite this as x to the 1 over n to the nth power. And so now I'm going to apply the chain rule to this. Okay? So g prime of x is equal to m times x to the 1 over n to the m times the derivative of the inside right? Well, we already know what that is because we just figured it out up here. So we can rewrite this. What's the derivative of that? Well, derivative of the inside is this. So it's going to be 1 over n x to the 1 over n minus 1. And so now if you combine these, what do you get? You get m over n, and this becomes what? This is going to become x to the m over n minus 1 over n times x to the 1 over n minus 1. Now, if you combine these two using the rule of exponents, property of exponents, then you have to add since these have the same bases, you add the exponents, right? Well, if you add the exponents, you're going to get a minus 1 over n and a plus 1 over n. So those are going to cancel out. And so what do you get? Your final answer is going to be m over n, x to the m over n minus 1. So there you go. Have a great day.